Okay, so we're going to wrap up our polygons, our straight-sided figures today, and transition into circles, because circles are really the main ingredient in our trig. So we've been talking about triangles, and triangles are actually a part of a larger group of figures called polygons. Polygons are anything with straight sides, or line segments as sides. And of course, the triangles are the most simple of those. It's the simplest two-dimensional figure that can be formed. It's what we call a closed figure. So a triangle has three sides. Bigger than that, four sides, of course, would be the next biggest one. Is anybody talking about what those are called? Squares. Well, square would be a special type of one. Trapezoid would be a special one. Quadrilateral. Now, just like we talked about, special triangles like isosceles and equilateral and right triangles and acute and obtuse, there are, of course, all sorts of different classifications of quadrilaterals. Parallelograms are probably the simplest one. A rectangle, of course, is just a parallelogram with right angles. A rhombus is just a parallelogram with all four sides equal. And of course, a square is all of those. It has all four sides equal and right angles in it. But then we also have special quadrilaterals like our trapezoids. We also have kites. And a kite, instead of two adjacent sides being equal, instead of two opposite sides being equal, like in the parallelogram, opposite sides are equal. In a kite, two adjacent sides are equal. John. Bigger than a quadrilateral is a pentagon. Has five sides. There's a pentagon. It has five sides. Very ugly pentagon. Now, somebody like, what the heck is that? You're used to seeing a pentagon drawn like this, right? That's what's called a regular pentagon. A regular polygon has all sides equal, but also all angles equal. I'd be thinking, well, if all the sides are equal, don't all the angles have to be equal? Oh, no. So I can have a regular pentagon here. Those three sides are equal, and guess what? Those sides are equal too, but the angles are not. So that leads us to something called concave and convex. Convex is what we're used to. Well, this one right here, that's convex. Concave is where one of the sides is caved in, like this one here. That's concave. Does that make sense? Now, of course, bigger than a pentagon, we have hexagon, which is six sides. Now, septagon or heptagon are both words that have been used for seven-sided construction. We don't hardly ever use seven-sided, so we're going to skip it. Next is octagon, which is eight. You'll occasionally run into a nine-sided, of course, is nonagon. Occasionally run into a 10-sided one, which is decagon. And then, no, dieci is Spanish. What's that? Deca is 10. Dodeca is 12. But realistically for us, we're not going to worry about working with anything really past the octagon. What's that?
What is Spanish 10? Who cares about Spanish? This is math.
I don't remember right now. D8 is dice or dice, isn't it? Italian is dieci. But anyway, one of the things I do want to talk about, we're going to focus on regular polygons because realistically in construction, you're pretty much always going to make a regular polygon. The regular polygons, as we said, all sides are equal, all angles are equal. So like a regular octagon, I don't know why my sides keep being longer the more I draw here, but would look something like that. If I could actually draw that, would look like a regular octagon. All the sides are the same, and all the angles are the same. So one of the things we need to figure out is, what are all those angles? Well, we talked about the internal angle sum before, right? Remember this? We talked about a triangle. It was the number of sides times 180 minus 360 degrees. Or we just did 180 times n minus 2 was the shortcut. Come on. Well, how many? This is a regular octagon, so n is how much here? 8. There are 8 sides, 8 angles. So 8 minus 2 times 180. That's 6 times 180, or 1,080 degrees, is the internal angle sum. These angles here have to add up to 1,080 degrees. What's that? Do you remember why? Because if I start here, if I'm going in this direction, I'm going to turn right there, correct? Then if I keep going this way, I turn there. By the time I get all the way around this thing, I have turned a total of 360 degrees, and I'm back in the direction I've got. So what that's saying is all these outside angles here add up to 360 degrees. But at each corner, these two angles add up to 180. So there's 8 corners times 180, minus the 360 that are outside the figure. And that would give you the same total if you did that. What I chose to do was do this as divide out 180 from both of those. So that's 180 times 8 minus 2, because 360 divided by 180 is 2. So it just makes it smaller numbers to work with when I do that. But technically the long formula is 180 times n minus 360. It's just simpler to do it like that. So now, of course, that is the internal angle sum. So what does that mean for each of those angles? Well, I have to divide that by 8, which is 135 degrees for each angle. So now here's the question. If I have an octagon where every internal angle is 135 degrees, does that mean it has to be a regular octagon? Is that a regular octagon? No. All those angles, 135 degrees? You bet they are. In fact, it's one very common variation for both, well, mainly for octagons. It doesn't work with hexagons. But for anything that has sides divisible by 4, like octagons, occasionally with dodecagons, 12-sided figures, if you're doing them in construction, it's a common variation rather than just having standard every side the same to do, yeah, I gotta use a different page to have a little more room here. Every other side longer, like this. So it's still an octagon, but it's not a standard octagon, obviously. Now in this variation, it doesn't look, oh, it looks like it's a square with the corners chopped off. But if you did it as a, I don't know if I could even come close to drawing a 12-sided. I don't think I'm even going to try to draw a 12-sided figure. No, it didn't go over it. Something like that, where it looks like a hexagon basically with the corners chopped off. In fact, that's probably the easier way to draw it. Well, if that looked like a hexagon. But anyway, you guys get the picture, right? That is a common variation in construction, is to take that figure that's got sides divisible by 4, and every other one is a little bit different length. So anyway, if I have a hexagon then, and pretend I can actually draw a regular hexagon here. Okay, screw that. We'll try again. Well, you're going to pretend a little bit. Pretend that's a regular hexagon. Tell me how big that angle is. Then you know, let's figure that out quick. What'd you get? 120 degrees. Good. Anybody get anything different? So just 180 times 6 minus 2, which is 720 degrees, divided by 6 is 120 degrees each. Perfect. Well, we want to focus in on our quadrilaterals. Pretty much everything we build is going to be 4-sided. One of our main variations on a quadrilateral, or one of the very main special quadrilaterals, is a parallelogram. We haven't necessarily officially defined a parallelogram. What are the unique properties of a parallelogram? What can you tell me about a parallelogram? Opposite sides are parallel. That is the definition of a parallelogram, is that opposite sides are parallel. Those two sides are parallel, and those two sides are parallel. Very good. Now you said something about equal. What's equal on them? Opposite sides are equal. These two sides are equal, and those two sides are equal. Then you said what, Sean? Opposite angles. This angle and this angle are equal. This angle and this angle are equal. There's one more relationship that we have. What's the relationship there? Equal 180. They're supplementary. Because these lines are parallel, right? So they either have to be equal or supplementary. They are supplementary there. Now, unfortunately in construction, most of the time for building parallelograms, that means you didn't do something quite square. But there are some unique features of parallelogram. One is, if we cut it corner to corner, you know, we looked at some special things we got when we cut isosceles and equilateral and right triangles. If we cut a parallelogram like that, what happens special about it? Well, this side and this side are the same, this side and this side are the same. Guess what? This side's equal to itself. we've got two triangles that are equivalent or congruent. They're equal triangles. And that's actually a feature of any regular polygon. Parallelograms?
Like way out, down to the bottom, just to make it look.
Yeah, I mean, if they do it, there's actually little formulas, there's golden ratios and stuff like that, aspect ratios that they use that if you're going to make it off square, make it at least this far off square so it looks intentional and not accidental. Yeah, I've seen it done several. I've done a few of them, off the side of a house where you actually angle it in. Trapezoids are probably more common, but I've done some parallelograms. A lot of times it's around features like trees or things like that. Or I've done a lot of octagons on decks.
We built one around a tree. I can't remember how many sides it had. I was working at a canoe tubing kayak.
Sure.
But he just started cutting an angle.
Yeah.
And he used the same angle all the way around.
Yeah, just wherever it came out, that's what it came out.
So
Anybody here live over by Weyerhaeuser?
Oh, what?
Over by Weyerhaeuser, Bruce, Lee Smith. There's a bar called Wojo's. It's called Bottoms Up on Highway 8 over there. I did a deck behind there a few years ago that was, I got to build around the trees, and that was a lot of fun.
Is that right on Highway 8?
Right on Highway 8, yeah. Right where W goes off of Highway 8 there. But anyway, anytime you have a regular polygon, if you go from one vertex to its opposite vertex, what do I mean by its opposite vertex? Well, that means no matter which way you go around the figure, you're going to go through the same number of sides. 1, 2, 3, 4 sides. 1, 2, 3, 4 sides. So that has to be its opposite vertex there. It'll cut it into two equal figures. Now, these are not obviously triangles. They are pentagons, but they are equal. In fact, I cut it this other way. Now I've got 4 equal triangles. No, I don't. I have 2 pairs of equal triangles, I should say. This one and this one are equal. That one and that one are equal. Same here. Cut it like that. Now, because this was actually regular and the parallelogram wasn't completely regular, all 4 of these will be equal. In fact, as we keep going, and you get it all down to triangles that are all actually equivalent. That'll come later on. One that does occur often enough in construction is a trapezoid. Usually it's a regular trapezoid, sometimes sunrooms. I've seen additions off houses done like this. Bay windows or port windows are often built as trapezoids, or almost always built as trapezoids, unless you get really fancy and go multi-sided. But we're going to go with the generic trapezoid here, so notice that the 2 angled sides are not the same. The distinguishing feature of a trapezoid, of course, is the parallelogram has 2 sets of them. The trapezoid has 1 set of parallel sides. We talked, when we found the area of a trapezoid, we went halfway down one side, and what we talked about was cutting off that triangle and flipping it up. Then doing the same on the other side, cutting off the triangle and flipping it up. Well, if you go halfway down the sloped sides and connect it with a line, that would have been that length of that rectangle formed by flipping up those triangular pieces we chopped off. When we did this, that length actually has a name. It is called a median of a trapezoid. A median. It's going, well, its length is going to be the median, or exactly in between the length of the 2 bases. The 2 bases are the 2 sides that are parallel. For example, let's say that this is 18 inches, and this down here is 32 inches. 18 plus 32 is 50, divided by 2 is 25. 25 is exactly between 18 and 32. It's the median, or middle point, between 18 and 32. And that's really what the word median means, is middle. Median means middle.
Yep. I understand that. I just don't understand how you got that.
18 plus 32. I took the two bases, added them together, and divided by 2.
Okay.
Let's have you work on a little bit here for a minute. 528. Now this is actually going to be in the unit exercises 1 through 24.